Have you ever really looked at the metal case on your phone, or the coins in your pocket, or even something as simple as a paperclip? They're all so perfect, so identical, right? Well, today we're going to pull back the curtain on the incredible and kind of hidden world of die design that makes it all possible. Let's jump in.
So here's the big question. How do you get that kind of perfection? Not just once, but millions and millions of times, and at like lightning speed. It seems like it has to be magic, but it's not. It is a brilliant piece of engineering that is literally all around us. And the whole thing starts with an idea you've probably used in your own kitchen. Think about it. You press a shaped cutter into dough, and bam, out pops a perfect cookie. Okay, now just imagine doing that with a thick sheet of steel, using a tool so powerful and precise it can stamp out parts for a car engine. That's exactly where we're going. All right, so here's what we're going to cover. First, we'll look at this industrial cookie cutter. Then we'll get into the physics of how you actually cut metal, a process called shearing. We'll find out the difference between punching and blanking. It's a cool distinction. Then we'll open up the die toolbox to see the more advanced stuff, talk about designing for efficiency, and even touch on how you can bend and shape metal too. Okay, so let's meet the two stars of the show, because in this industrial process, it's not just one tool, it's actually a perfectly matched pair that gets the job done. And here they are, the punch and the die. The punch is the part that moves, coming down with an incredible amount of force. And the die is the stationary block below it, with a perfectly matched opening. When these two meet inside a massive press, they act like a pair of super-powered scissors, capable of shearing right through solid metal. Now, you might be thinking the punch just, slices through the metal like a hot knife through butter, but the actual physics are way more interesting. It's not really a cut, it's more of a controlled break. The technical term is shearing. The key phrase there is controlled fracture. So instead of a smooth slicing action, the punch and die apply this immense, super focused pressure from opposite sides. And what that does is it forces the metal to just cleanly snap right along a predetermined line. It's a perfect engineered break. Let's break it down. First, the punch makes contact and starts to push down or deform the metal. Then, as that pressure builds like crazy, tiny little cracks start to form at the exact same time, one on the top edge by the punch and another on the bottom edge by the die. And finally, this is the cool part. As the punch keeps moving, those cracks race towards each other and meet right in the middle, and snap, the piece just breaks free. That entire thing happens in a blink of an eye. Now, here's where it gets really interesting. That single action, shearing a piece out of metal, can actually have two completely different goals, and it all depends on what piece you decide to keep. It all comes down to this simple question. What's the product and what's the scrap? If what you need is the big sheet with the hole in it, say for a computer case where you need vent holes, that's called punching. The little piece you pushed out, that's just scrap. But if that little piece you just pushed out is your product, like a coin or a washer, that process is called blanking. And now the big sheet with all the holes in it is the scrap. It's the exact same physical process, just with opposite goals. So simple punching and blanking are just the start. I mean, they're the building blocks. To make more complicated parts efficiently, engineers have come up with a whole toolbox full of incredibly clever die designs. I mean, why use two presses when you can get it all done in one? A compound die is a perfect example of this. It's designed to do multiple cuts at the exact same time in one single stroke of the press. So for example, it could punch out the center hole of a washer and blank out its outer circle all at once. Super efficient. But what if you need to take that to the next level? What if your part needs, say, multiple holes, and they're all different sizes, and it also needs to be cut out from the metal strip? I mean, doing that one step at a time would be way too slow. There's gotta be a better way, right? Oh, there is. It's called a progressive die, and it is basically a miniature factory packed into one tool. A long strip of metal feeds through it, and at each stop, or station, a different operation happens. Station 1 might pierce a tiny hole. The strip moves, Station 2 punches a bigger hole, the strip moves, and on until the very last station blanks the now finished part out of the strip. And here's the magic. Once the strip is all the way in, every single stroke of that press produces one perfectly completed part. It is the peak of mass production. So as you can tell, this whole game is about efficiency. But that efficiency is totally dependent on absolute, almost microscopic precision in how the tools themselves are designed. Probably the single most critical factor is something called die clearance. This is the tiny, tiny gap between the edge of the punch and the edge of the die. We're talking about a space that's often just a fraction of the thickness of a human hair. And getting that gap exactly right, well, it's everything. And this shows you exactly why. If you have the proper clearance, you get that clean, controlled fracture we were talking about. You get a perfect part, and you put less stress on your very expensive tools. But if that clearance is even a tiny bit too small, you're not shearing the metal anymore. You're basically just tearing it. That creates a nasty, rough edge. It takes way more force, and it will absolutely destroy your tools. So yeah, precision is a really big deal.
And that precision affects efficiency in another huge way: waste. Because in manufacturing, wasted material is just wasted money, period. So when designers are figuring out how to stamp parts from a sheet, they aim for what's called an economy factor of at least 60%. What that means is they're making sure that a minimum of 60% of that raw metal strip actually becomes useful parts, not just scrap heading for the recycling bin.
Okay, so far we've pretty much just focused on cutting things apart. But this same basic technology, applying massive, controlled force with a punch and die, can also be used to shape metal without cutting it at all. And that brings us to bending and drawing. In this case, the punch and die are not designed to fracture the metal, but to stretch and reshape it permanently. So, by carefully controlling that force, a flat sheet of metal can be perfectly folded into a complex bracket, or even stretched into the seamless body of a soda can, all without a single cut. And this quote really sums it all up beautifully. The technology itself provides the tools, but the sheer complexity and, honestly, the elegance of the parts that can be made is really only limited by the creativity and the ingenuity of the engineer designing the die. It's a true blend of hard science and creative art. So seriously, take a second, look around you right now. Look at your desk lamp, your computer case, the metal legs on your chair, the buckle on your belt. How many things in the room with you started out as just a flat sheet of metal? Once you know what to look for, you start to see this hidden world of engineering absolutely everywhere.